everyone, welcome back to chemistry. In this video, we're going to continue talking about molecules, and specifically we're going to talk about Lewis structures that we can draw for molecules and also for polyatomic ions. So you'll recall from a couple videos ago that we talked about how we can draw what's called a Lewis dot diagram for atoms to show their valence electrons in a more visual way. So say we had nitrogen, for example. Nitrogen's in group 5A, so it has 5 valence electrons, and we can show those electrons around nitrogen like this. We can go 1, 2, 3, 4, and 5. So now we've got those 5 valence electrons shown around nitrogen. Well, we can also draw something called a Lewis structure, and that allows us to show how atoms are actually connected in covalent bonds. So here's a molecule called ammonia. That's different from ammonium, right? Ammonium is a polyatomic ion, NH4+. Ammonia is NH3. So nitrogen bonded to 3 hydrogens. And we can actually see those 3 hydrogens here. These lines mean they're sharing electrons. Those are our covalent bonds. Remember, covalent means sharing electrons. And so we can actually show how those electrons are being shared and what our molecule kind of looks like. So using those Lewis structures. So it's pretty cool. And we can do this for polyatomic ions as well because, remember, polyatomic ions are, more than one atom bonded together with an overall charge. Okay, so kind of cool. So let's start with the simplest molecule, which is hydrogen. It turns out that in nature, hydrogen actually likes to bond with itself. And we'll talk about, there are several elements that like to do that, and we call them diatomic molecules. So there are elements that exist as diatomic molecules. They like to bond to themselves. We'll talk about that a little bit more in a little bit here. But starting with hydrogen, so a hydrogen molecule, H2, forms as the atoms move closer together and the positive charge of the nucleus of one of those hydrogens attracts the electron of the other hydrogen. So remember, hydrogen's in group 1A, right? So it has 1 valence electron. And as these hydrogen atoms move closer together, they actually end up being able to share these 2 electrons. Why do they want to share those electrons? Well, they want full valence shells. And remember, for hydrogen, the closest noble gas is helium, and helium has a full valence shell. So even though it doesn't have an octet of 8 electrons, it does have a full valence shell, because remember, that first sublevel, 1s, can only hold 2 electrons. So to be full means to have 2 electrons for that valence, or for that energy level. So each hydrogen says, well, I'd love to have 2 valence electrons. And they come close together, and then it's like, okay, well, we can actually just share those electrons. And when they share those electrons, that creates what's called a covalent bond. Yeah. So pretty cool stuff. So let me show you, these are kind of like bonding together. Okay. And then that molecule that's formed when that covalent bond happens is actually more stable than those 2 hydrogen atoms were on their own. Okay, so it's favorable for hydrogen to exist as a molecule bonded to itself. Pretty cool. So here is kind of a closer look at that. So I've color-coded this. There's 2 hydrogen atoms, and I've color-coded one of them blue and one of them red. So let's look at this for a second. So on the x-axis, we have, as we go to the right on the x-axis, the distance between our nuclei is decreasing. So what's that mean? That means our hydrogen atoms are getting closer and closer together as we move to the right on the x-axis. As we go up on the y-axis, our energy is increasing. So the higher we are on the y-axis, the higher our energy is. Okay, so looking up here at the top left, we've got two hydrogen atoms that are far apart, right? The distance between the nuclei is not very far. Or I'm sorry, is very far. And so they're far apart and there are no attractions. They're not close enough to have attractions, right? But as they move closer together, as the distance between the nuclei decreases, we now have some attractions that are pulling those atoms closer. Why? Well, each of those hydrogens really wants to share electrons because they want to be like the noble gas helium. They want to have that full valence shell. They also, the nucleus in, let's say, just for an example, in the blue hydrogen, there's a positive charge in that nucleus that's attracted to the negative charge in that red hydrogen, or from the electron in the outer shell of that red hydrogen. So as the distance between the nuclei decreases, as those hydrogens get closer together, they form a molecule because they say, hey, we could share those electrons and then we'd both be happy. And then you'll notice that their energy has gone from being pretty high to being a lot lower. Yeah. So that's why it's favorable for hydrogen to exist as an H2 molecule, is because it decreases the energy of that molecule. It's making it more stable. Okay, so a molecule can be represented by a Lewis structure, which we talked about, in which the valence electrons of all of the atoms are arranged to give octets. Or let's modify this, or full valence shells. Remember, helium is an example of something that's not going to have an octet because it can't. It can only hold 2, but that's okay because 2 is full. Okay. So the shared electrons, or bonding pairs, and we'll use yellow for this one, are shown as 2 dots or a single line between atoms. And you'll usually see them as lines. So just kind of start getting in the habit of, when you see a line, that means that there are 2 bonding electrons there. So each of those lines represents 2 electrons that are being shared between those 2 atoms. If you want, you can draw in little electrons, right? So that you can kind of visualize that. If that helps, you can totally do that. I'm going to leave them off for now just so we start getting the habit, because sometimes, like more often than not, you're going to see it depicted like this. And you're just going to have to start remembering that one line is 2 electrons. Okay? So each of those lines is 2 electrons, and those electrons are being shared between the atoms. And those are also called bonding electrons, or bonding pairs. Okay, and then there are also non-bonding pairs. So electrons that don't participate in bonding, those are called lone pairs or non-bonding pairs. And I'm going to show those in blue. And what we do with those is we just keep them on the outside of the atoms. All right. So for Lewis structures, we just said that a molecule is represented by a Lewis structure in which the valence electrons of all atoms are arranged to give octets, or full valence shells. So let's try this with fluorine. So let's zoom in a little bit. Looking at fluorine, remember, each fluorine has how many valence electrons? Yeah, 7. Why? It's in group 7A. So it really, really, really wants to be like neon. It only needs 1 more electron. Each of those fluorines only needs 1 more electron in order to have full octet. It has 7, each of these fluorines has 7 valence electrons, and it wants 1 more. They want 1 more. So they get close together and they're like, you know what? Let's just share. Let's share our electrons, and then we can each have that octet. So that's exactly what they'll do. So here I'm going to highlight our lone pairs in blue again. So those didn't go anywhere, but we want to bond these 2 electrons because we only want 1. Each fluorine only wants 1 more electron, right? So we don't really, those lone pairs can kind of just hang out. We still want them because we want that full octet, but we do want to bond these two middle ones because we want to share those electrons. So once those electrons are shared between those two fluorines, we've created our covalent bond. And that covalent bond, remember here, that's 2 electrons. Anytime you see a line, that's 2 electrons. Okay, and then this isn't a bond, it's an equal sign. And so it's just showing you that, hey, this is, let's do this color. This is our fluorine molecule, which is F2. Yeah, so fluorine is another one that exists as a diatomic molecule. It's an element that is a diatomic molecule. It's so much easier for fluorine to share those electrons with another fluorine to achieve that lower energy state to be more stable. So it will, yeah, pretty cool. Okay, so I promised we talk about this. So elements, there are some elements that are diatomic molecules, and these are just elements that we just see in nature existing as diatomic molecules. They like to bond to themselves. So there are 7 total. There's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And these all are diatomic molecules. There's a couple ways to remember this, and you will want to remember this. So I was always taught to the word Hofbrinkel. I don't know, it's not really a word, but Hofbrinkel. That just is a way of remembering what elements are diatomic molecules. So there's hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Sorry, this is an L. This is chlorine. So Hofbrinkel. There's another way of remembering it, and that's if you look on the periodic table, they actually make a 7. Hydrogen, again, is always kind of an exception, so you just have to remember that hydrogen is part of it. But there is a 7 on your periodic table, just like this. Or maybe an upside down L, depending on how you look at it. The 7 helps because there are 7 of these diatomic molecules. You have to include hydrogen for that to work, though. But it creates a little 7 on your periodic table. So the first 4 halogens, right? Fluorine, chlorine, bromine, iodine. And then the NO, nitrogen and oxygen. So whatever way works for you, or a mixture of both. Okay, so let's just go ahead and look at an example. How do we actually draw these Lewis structures? And I'm actually going to go over here and do it. So the one that I want to draw is CH4. What is that? That's methane. And you might have heard of methane. It's a very common greenhouse gas, very strong greenhouse gas. Cows produce a lot of it after they eat. So how do we actually draw how this is bonded together, what it looks like? So the way I do it is, first I like to put all of my atoms down on paper. So I have carbon atoms and I have hydrogen atoms. What atom do you think is going to go in the middle of our Lewis structure? I guess I already drew it, so spoiler. But yeah, carbon, because I have 1 carbon and 4 hydrogens. So I guess I'll just put these hydrogens around it like that. Oops, I kind of want to scoot this up here a little bit more. Okay, so I have all 4 of my atoms, all 5 of my atoms here. Now I want to draw the Lewis dot diagrams. Remember, I want to show how many valence electrons each of these has to contribute, because I know they're going to eventually share some, right? That's how they form this compound, this molecule. And remember, we know it's a molecule because it has 2 nonmetals. So it's covalent. So we have, let's go ahead and draw our valence electrons. So hydrogen, each hydrogen has how many valence electrons? Yeah, 1, it's in group 1A. So let's go ahead and draw those valence electrons. I'm just drawing them there because I know that they're going to kind of bond with that middle carbon, so I'm just going to draw them there. You will just kind of develop an intuition for where to draw them in the future. And then for carbon has 4 valence electrons, right? It's in group 4A. So I'll just start here and draw 1 on each side of carbon. Okay, so how do these actually bond together? Well, remember, we want the goal, the reason that this forms is because carbon wants 4 electrons. It's in group 4A. It really wants 4 more so it can be like neon. And hydrogen really wants 1 more to be like helium. So what they're going to end up doing is they're actually going to share these electrons. And they're going to say, you know what, let's just share and then we'll all be happy. We'll all have our full valence shells. For carbon, that means an octet. For hydrogen, that means 2 electrons. Right? So now if you look at each of these atoms, you can see that each one has a full valence shell because they're sharing those electrons. So just looking at carbon right now, how do I want to do this? Let's just look at carbon is sharing these 2 electrons. It's sharing these 2 electrons. It's sharing these 2 electrons, and it's sharing these 2. So how many total electrons are around carbon right now? Yeah, 8. Yeah, pretty cool. What about for each hydrogen? So let's just look at this hydrogen right now. This hydrogen has how many electrons? Yeah, 2. So that hydrogen is happy, right? So just to clean this up a little bit. So actually you could just leave it like this. And then you can show, you can do a cleanup like this. You can show CHHHH. Remember, we said that when these atoms are bonding, we can represent those bonds as lines. So to draw our Lewis structure, we have 2 electrons bonding here, 2 electrons bonding here, 2 bonding here, and 2 bonding here. So this would be our Lewis structure. We don't want to show it like this because that's not really a Lewis structure, but it helps us understand maybe how we got to here. So if you want to show that first step, you can. And in fact, I would encourage you to show some of your work, some of your thinking, so that you can show how you got to the final answer. Okay? All right, and we'll do some more examples. So if this isn't making sense yet, that's okay. One question actually, real quick, that I get a lot with these is like, how did I know to put carbon in the middle? For something like this, for this first example that I did, carbon's in the middle, and that might be a little bit more obvious because we have 1 carbon and then 4 hydrogens. But sometimes it can get a little bit tricky and we can have maybe like 3 carbons and, you know, I don't know, or 2 carbons and 6 hydrogens or something like that. And then it gets a little bit more like, which one goes in the middle? And I will say I don't have like a great trick for it. But here they say that the central atom is the atom in the formula with the least number of atoms. And I think that's generally a good way of looking at it. So say you had C2H6, that carbon has less atoms than the hydrogen, or there are less carbon atoms than hydrogen atoms, so you would put that carbon in those carbons in the middle, and kind of orient the other ones around it. So I don't know, not kind of a fuzzy answer, but you'll get used to it as you do more, okay? I promise. Okay, so drawing Lewis structures. So electron dot formulas for common molecules like methane, ammonia, water are shown here, right? This is just like we saw above. So here's that methane that we drew out. How did we get to this nitrogen here? Well, let's see. Do they have, I thought they had an example. No, I want to show you this first. So let's try to draw that NH3, that ammonium. So let's draw the Lewis structure for ammonia. Did I say ammonium? I'm so sorry if I did. I meant to say ammonia. NH3. Okay, so we want to draw this Lewis structure. So what are we going to do? Okay, looking at this, the first thing I like to do again is to put all of my atoms down on the paper. So I have 1 nitrogen and 3 hydrogens. So let's just put nitrogen in the middle, right? It has the least number of atoms, or we have the least number of nitrogen atoms. And then I guess let's just put our hydrogens around it. And I kind of know where these are going to go, so that's why I have them all nice and neat like this. It's okay if you draw them kind of wonky at first, okay? As long as I can see your thinking and I can see that you have the correct number of electrons on your paper, you have the correct things bonding to the other correct things, that's fine. So you could have drawn your hydrogen up here, you could have drawn it over here, and I'll just correct you just so that you know for the future, but I wouldn't mark you wrong for the first time that you did it. You know what I mean? Okay, so we have our nitrogen bonded with our hydrogens around it. Oh, gosh, talking's hard. So for our nitrogen, let's go ahead and draw our valence electrons. So we have nitrogens in group 5A, so we have 5 valence electrons. So let's just go ahead and draw those. So we have 1, 2, 3, 4, and 5. We'll put them right there. And then each of our hydrogens has 1 valence electron. Okay, so the way I've drawn this, I've kind of led the witness a little bit, but that's okay. So how are we going to bond these electrons? Well, nitrogen has these 3 lone electrons, these 3 kind of lonely electrons, and they look like they're perfect for sharing. Hydrogen also has 1 each, right, that looks like it could be shared easily. So let's go ahead and say that these 2 are being shared, these 2 are being shared, and these 2 are being shared. What do I do with these last 2? Yeah, they kind of just hang out. They're now what? What do we call those? Yeah, that's a lone pair. So let's show that in blue, and then maybe lone... you know what? Actually, let's make this red. Lone pair of electrons. Yeah, and that's okay. We can have lone pairs. And the reason that we can have those is because everyone is happy in this molecule right now. So let's just do a check. So once I have all my electrons down on paper, I like to check that every atom, and I've bonded them, I like to check that every atom's happy. So for my nitrogen, I'm looking at that nitrogen and I'm saying, okay, do I have 8 valence electrons around my nitrogen now that I'm sharing these electrons? Because remember, that's the whole reason we did this. We want each atom to have a full valence shell. So for nitrogen, that's 8. So how many electrons are around this nitrogen right now? Yeah, we've got 2, right? We've got 4. We've got 6, and we've got 8. Yeah. So remember, that's why they're bonding. Okay, so that they can share those electrons and have a full valence shell. What about our hydrogens? Hydrogen's kind of a unique case because it only wants 2 to be like helium. So we got 1, 2, 1, 2, and 1, 2. Yeah, so each of those hydrogens is happy as well. Great. Okay, so now is the cleanup step. So let's go ahead and clean this up. What does this actually look like if we were to represent it as a Lewis structure with our... Why do I always want to draw that far out? They should be equally spaced. So we're going to have our lines and our lone pair. Remember, the lines are 2 electrons each. 2e minus each. Now we've drawn our Lewis structure for ammonia. Yeah, NH3. Okay, so let's try this one more, and then we'll pause and come back for part 2, because this video is getting a little longer. So let's draw the Lewis structure for PCl, phosphorus trichloride, which is used in the preparation of pesticides and flame retardants. So try this out on your own, pause the video, and we'll come back and talk about it. Okay, so we have phosphorus, 1 phosphorus, and 3 chlorines. So how'd you draw this? Yeah, we're going to put the phosphorus in the middle, I guess, and then I think I don't know, I'll just put the chlorines around it like that. Okay, so for phosphorus, let's see, how many valence electrons does phosphorus have? Yeah, it has 5 valence electrons, so let's go 1, 2, 3, 4, and 5. Okay, and then chlorine, how many valence electrons does each of these chlorines have? Yeah, chlorine's in group 7A, so each has 7 valence electrons. So let's go ahead and draw those. We got 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. Okay, again, because I've drawn these 1,000 times, I know kind of where to put the electrons, but you could have put them in different areas. That's okay. And then you're just going to have to do kind of some, finding to rearranging to kind of figure out how to bond these well. I've led the witness a little bit, though, and kind of arranged it in a way that is useful or kind of quicker for me. Okay, so how are we going to do this? Well, remember, each of those chlorines has 7 valence electrons. So how many more do they want in order to get to their full octet? Yeah, each chlorine wants 1 more electron. What about phosphorus? It has 5. How many valence electrons does it need to be like the nearest noble gas, argon? Yeah, it needs 3 more. Because 5 plus 3 is 8, excuse me. So all of these want an octet. So how are we going to do that? Well, I'm looking at these here. Oops. These here, and I'm noticing that maybe we can share those, right? So the chlorine can share its electron and the phosphorus can share its electron. Same thing here, right? We can share those. We can also share these. And let's just do a check. So if we're sharing those electrons, we want to make sure that all our electrons that are shared, and let me just show this as a line, actually. Choo, choo, choo. Okay, so let me just do this with, I don't know, let's do green, I guess. So that chlorine on the right there, just looking at that, it's got all of these electrons now. Remember, because it's sharing these two right here, both of those. So how many electrons are around that chlorine? 2, 4, 6, and 8. Yeah, 8 total electrons. So let's write that down. 8E minus. What about this chlorine? Yeah, 8 also. And this one? Yeah, 8. Okay, so they're all happy, right? Okay, and this is going to get a little messy, but we can do it. So, and then what about our phosphorus? We've got these two. We've also got this one, these two, and these two, and these two, and that's it, right? So in that yellow circle, how many electrons do I have? 2, 4, 6, and 8. Yeah, 8 electrons. Awesome. Okay, so let's go ahead and clean this up. So now I know how these are going to look when they connect. So I got Cl, Cl, P, and Cl. Remember, I'm going to show those bonding electrons with a line. So let's just do that. 2, 4, 6. And then I still have that lone pair. Don't forget about them. What else is missing? We need to draw the rest of these lone pairs on our chlorines. Don't forget about those. Okay? Don't forget about those. They're very important. If you don't draw them, we don't know that they're there. With the hydrogens, why didn't we have those around? We didn't have any of those. Why? Yeah, hydrogen only had 1 electron each to share. Okay, so they didn't have any other lone pairs or anything we had to worry about. But these do. Okay, so this would be your Lewis structure for PCl3, phosphorus trichloride. Yeah. Okay, I hope that's helpful. Join me back here for our next video and we'll go over some trickier ones.